Hello, I'm Carlos Frojuca from the São Paulo Federal Institute in São Paulo, Brazil. First of all, I would like to thank all the organizers for this wonderful event. And now I'm going to present you um, a short presentation about a method to design mechanical transducers for resonant mass gravitational wave detectors, a work make in collaboration with Fábio da Silva Bortoli from the São Paulo Federal Institute and Nadia Simão Magalhães from the Federal University of São Paulo, both institutions in São Paulo, Brazil. What is our work? Our work is how to make the design of transducers for gravitational wave resonance mass detectors. But what's the problem of that? Because you need to, this kind of detector is a mass. When the gravitational wave passes through, it makes the mass to vibrate. But this vibration is very small, 10 to the minus 18. And then to amplify this movement, we put on the surface, in some part of this mass, another set of transducers, mechanical transducers, that amplifies mechanically the vibration on the surface. The amplitude of the vibrations are amplified by a factor of the square root of the mass ratios between the first mass and the second one. But one of the problems is to know what's the exact mass of this resonant transducer, because sometimes it's not very easy to see what's the exact mass, because part of the mass is included in the spring. It's not like this lumped model here, because in this kind of scheme you can see here the spring, that is the mass. But for example, in the Scheinberg detector in Brazil, is a spherical one. The mass is the sphere itself, and it's not easy to know what's the effective mass and what's the spring constant. The same thing applies for the other resonant modes of the transducer. In this case here, we have a sphere suspended, a suspended sphere, cooled down to very low temperatures, and on the surface we add some mechanical oscillators. But the problem is how to exactly know what's the exact effective mass and what are the right spring constants, because sometimes the springs and the masses, they are interconnected. For this example, like this one, this is connected to this piece here is connected to this sphere. These are the springs. This is the second mass. And the third mass, it's a membrane, a diaphragm. It's hard to know in this case the diaphragm what's the mass and what's the spring constant of this case. And then it's our main purpose here is to find a way how to design that and find the exact numbers, the exact bandwidth of the system. What's the methodology? Where analyze the massive sphere, the sphere with the transducer connection holes, the sphere with the transducer connectors, and the suspension hole with that. And what we have done, we set, we know the mass of the sphere. The effective mass is already calculated by some other words. We use that effective mass in the lumped model. We have the mass in the membrane. You can do that also by effective calculation. And what we have done, we start to change in the mass of the intermediate resonator. And what's the meaning for that? It's because when you have the beta coupling of all the modes, you're going to have this modulus bandwidth. And these are the frequencies of the system. Because you have a hole in the sphere, the frequencies are not degenerated anymore. We have 6 modes for the sphere. We have 6 modes for one transducer and 6 modes for the second transducer on the sphere. Then you have a set of 17 modes. And we got here a quintuplet, a singlet, another quintuplet here, a singlet, and another quintuplet. And we are changing the mass of the secondary resonant until we got the smallest bandwidth. That was what you get here, and this bandwidth here. And then we know that we have the right effective mass in this case. Yeah, that's what you have done, and you are quite confident that's the right way to do it.